Good afternoon, everyone. We're Group 2 and we're here to present our drone for the control engineering assignment. So our drone's use case is for photography. As such, we need to have a drone that is capable of maintaining stability under external disturbances as well as having good rise time, settling time, and little overshoot. If you look at the simulation circuit on screen, you'll see that we have our drone altitude transfer function as well as a wind disturbance transfer function. This wind disturbance transfer function will simulate the effects of external disturbances on our drone. On the left, you'll see that our input is our desired altitude, which is 10. So if we run our simulation, you'll see that with or without the disturbance, our drone does not simply settle at 10. It overshoots past 10 to around 15 and takes until around 10 seconds to settle to around 10 meters in altitude. As such, each of our group members have decided to individually create controllers in order to improve the performance of this system. Now we will introduce our group members. My name is Austin.
My name is Muazzam.
My name is Ahmed.
My name is Abdulaziz.
My name is Hassan.
My name is Mahmoud.
So you'll see in the end that we ended up going with the MBC controller because it had the best performance. So moving on to the individual parts.
Hi, my name is Muazzam, and this is my CE presentation for the assignment. And my part was the lead lag control system for our drone module system. So starting with the basic drone module system, as you can see, our desired altitude we put as 10, and we put a step function with the wind disturbance. It's a separate transfer function because it is a disturbance that's outside of the actual system. As you can see for the drone, we have the 0.249. We chose a random model of a drone with this exact weight, 0.249, and the M carry here would be the load, and the 0.3 would be the damping ratio, which was generally estimated according to some actual references, which will be given in the documentation. So this is our base system, and now I can show you the current values of the system without any control system applied to it. Let me share the screen. Okay, as you can see, these are our current values. So as you can see, the settling time is okay for the system, and the offshoot is a little bit high. It's like 4.9 would be almost 15% of the original value. The offshoot will be 15%. And for the with disturbance part, it is a little higher than the without disturbance, of course. And the rising time is somewhere around 1.4 and 1.1. So these are the current values that we get without using any control system. Now moving on to the actual control system design, that would be this. So this is the lead lag system. So what I did was I used the discrete transfer function for my control system with gain. I will show you the discrete transfer function and its values. Here, these values that you see, the numerator is 48 minus 40, denominator 1. How I got these values was by iteratively tuning the transfer function so that I could find a good balance between reducing the rising time and the overshoot as well. So this is what I ended up with. Going back. So this is what I ended up with, and the gain also you can see here. So this is the model. You can see the input from the control system, and then you have the transfer function of the drone and the wind disturbance, and now running the actual simulation. Okay, so this is the actual simulation of the system after using the control system. So as you can see, it's a major improvement from the uncontrolled one. The overshoot is quite significantly reduced. It's like from 15% to almost 10%, as you can see here. And the rising time as well, it went from almost 1.9 to 1.3 seconds. So these are major improvements in these areas. Also, the settling time is also much stable and much less now. But the only critical error here would be, let me zoom in. If you look at the settling area, you can see that there are unstable oscillations and the system never actually reached a good steady state. So this is because of the earlier values that we saw that we put in the discrete transfer function, 1 in the denominator, which means that the controller's pole is going to be -1, which is only marginally stable. It does improve the transient response, but it fails to achieve a good steady state. So in summary, you'll say the controller was successful at making the drone faster, but the next logical step would be to fine tune it more, fine tune the pole and zero placement to eliminate these oscillations so that it ensures a stable and accurate performance. Thank you very much.
Good afternoon. Today I'll be presenting my part of the individual assignment. So for my part of the individual assignment, I've decided to do a comparison between two PID controllers. As you can see at the bottom, we have our uncontrolled drone system being fed into a scope. This way we'll be able to use it as a benchmark for to check the performance of our two PID systems. So for our PID systems, we'll have the PID controller itself, which is fed into the drone system itself, okay? So we are using the same setup for both of the PID controllers, just with different coefficient values. For our first PID controller, we'll be using a proportional gain of 40, an integrated gain of 2, and a derivative gain of 4. While for our second PID controller, we'll be using a proportional gain of 80, an integrated gain of 2, and a derivative gain of 6. So once we run the simulation, we can check this in order to check the performance of the two PID controllers. So first off, this orange line is our uncontrolled drone system. So when it's uncontrolled, the drone has a very high overshoot, as we can see, with a very long rise in settling time. Comparing to that, when we have our PID controllers, the performance of the system is very much improved by a lot. So as you can see, the overshoot is much lower while the rise in settling time is much faster. So if we take a closer look, you can see that comparing the two controllers side by side, we can see that PID2 has a low overshoot while also having a faster settling time and a faster rise time. As such, we should be using PID2 to control the drone moving forward. That will be all for my individual part. Thank you.
And now it is my part. Hello, my name is Hassan Ammar Al-Bakr Bakweri. My TB number is 074401. Now it's my part to talk about my unique enhancement into the circuit. And my unique enhancement idea is add a PID controller with fine tuning into the circuit. As you can see here, we have two transfer function, one without the PID controller and one with the PID controller. And so this is the PID controller, and as you can see inside the PID controller is the values. The values here. How I derive the values of the PID controller, where I use the PID tuner app. So this is the inside the PID tuner app in MATLAB. I customize the transient behavior and response time to get my goal, which is makes the waveform set at 10. Now now let's see the scope after we run it. So this is the scope after we run it. We see here that this is the waveform. You see that we have a greater system response after adding the PID controller, because you can see here the difference. And now we can talk about the main parameters about the drone altitude. You can see we have 4 main parameters, which is the overshoot, rise time, settling time, and final altitude. We can see here the difference that for overshoot, without the controller, it was 14, but now with the controller, now with the peak at 10, which is for the we reached our goal, and you can see the first improvement of the PID controller. And with the rise time, it was 1.9 without the controller, and it decreases until 1.058. For the settling time, it was 15.5, which decreases until 4 seconds. We see that this is a great improvement. For the final altitude, we have here the controller is still at 10, but we have a big gap error, which is 20 millimeter. And now with the bead, the controller is decreased until 2 millimeter. After showing the main parameters, like we see the BID controller has greatly improved the performance of the system.
Talk about building model controller. Is a controller method that very strong agent distribution, disturbance and uncertain test. Its main idea to create a sliding surface that makes the altitude error with the vertical velocity of the drone. The controller then keeps the system on this surface until the altitude reach and stays at the desired value. The controller works by weight switching if the system goes away from the sliding surface. The controller sends correction sign to bridge it back the journal test stability and accuracy hovering even with external. Let's show the simulation how it's getting. Simulation results show that SMC removes steady state error and keeps the altitude steady without large oscillations. That the velocity also goes to zero at steady state. The only limit that is rise time improving the small compared to the other controller like MPC. In summary, CMC giving the stability, accuracy, and strong resistance to disturbance, making it a reliable choosing for altitude controller. Thank you for watching. Summary.
Hello, my name is Ahmed Shahab Khan, and today I'll be showing you and going through the enhancement that I personally made to the pre-existing group transfer functions. So as you can see on the screen, there are the basic transfer functions as the group, which are desired altitude, and these. My main part or my main innovative idea was for the LQR controller, which is basically used as a linear system, and it has certain capabilities such as delivering fast transient response, zero steady state error, and a balanced control effort. Basically, it has dependency as a linearized model, and because of which we had to use only linear equations in the steady state space of the plant. It basically starts with a step input, which is the step command. Then the commanded reference altitude is compared with the actual altitude, and the difference between them forms the error signal. And later we have the state space representation for which the values are set in the editor. As you can see, there are 4 variables A, B, C, and D. The values are set in the editor, as you can see now. Later, this is after the steady state space of the plant. It is followed by an optimal state feedback by the LQR controller, which goes back into the summing junction. And later we have two scopes to see the output. So one is for without the controlled path. The second one is for the controlled response. So let's go ahead with the scope. All right, so as you can see, the LQR is almost reaching 1. The Y, which is the demultiplexer, if you zoom on the yellow line, you can see it's reaching an altitude of 10, which was the desired altitude and which is perfect as well. And it doesn't have any overshoot. It doesn't have the rise time is very fast, and the steady state error is just perfect. Next we can go to the control response scope. Okay, so here the blue line indicates the velocity, which shows how fast the drone becomes stagnant after reaching an altitude of 10. This is a very important condition because after it reaches the set altitude, it should be stable because it needs to take pictures, and stability is a very important criteria. The velocity should be 0. As you can see, it becomes 0, and it becomes stationary and doesn't move. Thank you very much. This was for my part.
Hello, everyone. I'm going to introduce my part, which is MPC. It stands for Middle Predictive Controller. So from its name, it's predict the future, and depend on it, it changes the calculation and output. Okay. So comparing to the rest, MPC is the best compared to the other controller we have. Okay. It's very accurate in all of terms. Okay. For example, if I want to explain it, it's like driving a car. Then when you see after 10 miles, there is a turn, so you start slowing down. It's the same concept. Okay. So now let me show the block diagram. Okay. So here I made one without a controller and one with the MPC, so we can compare between them. Okay. So let me show the controller design here. Okay, so as you can see here, we have the sample time equal to 0.001, and the prediction horizon is equal to 10, which means for how long in future you will predict. In our example, it's the 10 miles itself. Okay, and control horizon is equal to 5. Closed loop performance here it is, and state estimation and the input response, output response. Let me show the output. Okay, let me run. As you can see here, it's now the yellow one, it's without the controller, and the blue one with the controller. Okay, so you can see the difference when you zoom in. Okay, so this is the overshoot and the estimating time, everything. Settling time, I mean. Okay, so actually 5 minutes ago, everything was fine. Until now, everything's fine. But the values changed after I saved and open again. Okay, so excuse me to read the values from the screenshot I have. Okay, so as you can see here, I have the rise time is equal to 10 milliseconds. Okay, here, and overshoot is equal to 85 millimeter. Okay, and settling time is equal to 60 milliseconds, and the steady state error is extremely low. Okay, so comparing to the rest of the controller we have, MPC till now, it's the best controller we have from the overshoot or the rising time and the settling time, even the error response, steady state error. So that's my part. Thank you.